All right, before we jump into our method of joints to solve for these member forces, we need to get a little bit more information. We need to figure out what these angles are, and we're just going to use basic trig to fill those in. All right, if you were to drop an imaginary line down where there's 1,000 pounds of force is being acted on joint D, you would make an isosceles triangle that is congruent to this other triangle over here. So this would be 3 feet, this would be 3 feet. You could choose your poison. You could do Pythagorean theorem to figure out what that hypotenuse is. All isosceles right triangles are going to share the same angle on either one of these ends. That's going to be 45 degrees. You can just trust me on that one. All right, so that's going to be 45, and this is going to be 45. All right, if you wanted to do, the sine of theta, let's say this was theta sub 1, right? You want to do sine of theta is equal to SOHCAHTOA, right? So SOHCAHTOA, opposite over hypotenuse, all right? Or if you wanted to do, let's do tangent, that would almost be faster because we have those numbers right here. So let's say the tangent of theta, all right? The opposite over the adjacent, we know that that's 3 feet over 3 feet. Feet cancels out. So it's going to be the theta is going to equal the arc tangent, the inverse tangent of 1, which that theta is going to equal 45 degrees. All right, so A and C, those are both going to be 45 degrees. Right in here at joint B, all right, we've got a little bit of a smaller triangle. Okay, so if we drop this down right here, this would be 3 feet, and then this right here would be the 2 feet. So that's a little bit of a different triangle. Again, you could do the same thing right here where you could use tangent. So let's flip this over and say we want to do, let's say this is theta sub 2. All right, so the tangent of theta sub 2 is going to be equal to opposite over adjacent. So the opposite is 3 feet over the adjacent is 2 feet. That cancels out. So you're going to say theta of 2 is the arc tangent, tan to the negative 1 over 3/2. You put that in your calculator, and that is going to be something like 56.31 degrees. Okay, so theta 2, I'm going to erase that, call it 56.31 degrees. Okay, this is the same triangle right here. So right here, that's going to be 56.31 degrees. And you can ask your math teacher what this one right here will be. All right, I'm pretty sure it's going to be 180 minus these two numbers. What's left over is going to be right there. But we don't even need that for right now. We just, these two, or I should say these 4 angles will be enough to use for our method of joints to figure out the forces in the members. All right, now it's time for method of joints. And we're gonna redraw our truss so that we can get our free body diagrams for each joint and the forces that are reacting on them. You do this by erasing the middles, and we're going to assume that all of the members are under tension. And so if we get a positive number, it is in fact in tension. And if we get a negative number, that member is actually under compression. All right, we drew the arrows in class for tension with the these arrows of the member pointing at each other. And that's confusing because you think about compressing, like I'm pushing something together, but that member is like this pencil. It's under compression. So if I'm pushing from either end of this pencil, the member is actually pushing back in both directions to kind of like stop me from crushing this pencil. Okay, and then conversely, if I'm pulling the pencil apart from both directions, right, the member itself is kind of pulling back at me so that I can't pull it apart. And so that's why we have the 2 arrows facing each other when this member, this part of the truss, is under tension, and when it's under compression, the arrows would point away from each other. But we're going to erase all the middles of our truss. We're going to put those member forces pointing at each other, and that's going to that's going to communicate that we think each member is under tension. And again, when we do our math, if we get a positive number, it is in fact under tension. And if we get a negative number, it's going to be under compression, and we'll slap the arrows going the other way. Okay? Let's also label our members with the joints. So this member is going to be member AB. This one's going to be AD. This one is going to be BD. We're going to do alphabetical order here. This one's going to be DE. This one is BE. This is BC, and this is CE. All right? And so now we're just going to focus in on our starting point. We're going to start over here. We got the most information. We've got reaction forces. We've got the angle. All right, so we just have to try to solve for the component forces for member AD. And if we start with our Y forces, you can see that at this joint there's also the AB member, all right? But there's no Y component forces for member AB. It's just moving horizontally, so we don't have to worry about that, all right? So we just have to solve for the Y component forces for AD. And then once we do that, we can then move on. So we're going to redraw a free body diagram for joint A on another piece of paper, and we're going to dive into this. All right, I've redrawn joint A with its members and reaction forces right here. This is the free body diagram for it. Okay, and what I'm trying to identify is all of my forces that are acting in a Y direction, either up or down, and an X direction, either left or right. Okay, and so these three forces, those are pretty easy because they're moving horizontally and vertically. But AD is going to have component forces because some of this vector, it has a force acting in an XY direction, and then some of this vector has a force acting in the Y direction. So redrawing this part of the drawing like this, right? And you've got some forces of this AD. So an AD in the X direction, and we know it's going to be going positively to the right. And we're going to have some that's going to be ADY going in the up positive direction there. So in order to get all of the forces of vector AD of that member on this joint, you're going to have some ADX, and you're going to have ADX and ADY combining to make this member vector. Okay? And so what we need to do is we want to kind of put ADX and ADY in terms that we can solve. Okay? And so what we can also tell you is that if this is a 90-degree angle and this is 45, we know this is 45 degrees right here. Okay? And so now I've got a triangle where I can use my SOHCAHTOA to figure out ADX and ADY. So what we're going to do is we're going to solve or calculate ADX and ADY. We're going to use SOHCAHTOA. We're going to use sine and cosine for each of these. All right, so here's my theta. So I'm going to take the opposite ADX over the hypotenuse AD. So if I have ADX divided by AD, that's going to equal the sine of 45 degrees. Okay? And so when we want to, put ADX on one side of the equation, it's as simple as just multiplying both sides by AD. And so ADX is going to equal AD times the sine of 45 degrees. Okay? And right now we're just going to leave it as AD sine 45 degrees because what this is telling us is that this ADX it's a component force of AD, but it's going to be one of the X forces when we do our summation of all forces acting in the X direction, where right is positive, right? And we're going to set those all equal to 0. And so we're going to have 0 pounds, AB, and ADX. Those are all going to be set equal to 0. And we're going to do the same thing solving for ADY. And so we can use cosine to get adjacent over the hypotenuse, all right, putting everything in terms kind of like an AD. And so ADY over adjacent over the hypotenuse, AD, is equal to the cosine of 45 degrees. And again, you just multiply both sides by AD. And so that's going to tell you that AD cosine 45 degrees is equal to ADY. All right? And so now I've solved for ADX right here, and I've solved for ADY right here. And so now I have all of my forces in both X and Y directions, so I can use my equilibrium calculations, because I know that this truss isn't going anywhere, right? I can set these equal to 0 and solve for what is remaining.